Hello everybody, I am Mika Seppälä. In this video I discuss the inverse operation to differentiation. That is, I want to find functions whose derivatives are given functions. This is difficult, sometimes impossible, but it has many important applications. This leads to the concept of integration. By an antiderivative of a function, we mean another function whose derivative is that given function. Here in this picture you see graphs of two functions. One is an antiderivative of the other one. Which one is which? We will discuss this problem shortly. This video is an introduction to the concept of antiderivatives and starts a new area of calculus. The formal definition is the following. A function capital Case f is an antiderivative of a function small case f if capital Case f prime equals small case f. That is, if the derivative of the function capital Case f is the function small case f. Using this definition and the table of derivatives, it is easy to figure out antiderivatives for certain basic functions. For example, for the function x, an antiderivative is 1/2 x squared, but also the function 1/2 x squared plus 1 is an antiderivative because the derivative of 1 is 0. So this comes immediately out of a table of derivatives. And likewise, for the function cosine of x, an antiderivative is sine of x, but then we may also add any constant to sine and we get an antiderivative. So, for example, sine of x and sine of x minus 1 are both antiderivatives of cosine of x. In general, any function has infinitely many antiderivatives because we may add a constant which then may vary, and we get from an antiderivative new antiderivatives by this process. In the title page of this video we had the following picture. It shows the graphs of a function and that of its antiderivative. And our task is to figure out which is which. Now, the derivative of an antiderivative is the function itself. Therefore, if the red curve were to be the antiderivative, then its derivative would be the blue curve. But the red curve is initially increasing, starting from the left. Therefore, the derivative would have to be positive, starting from the left. The blue curve takes negative values when x is less than 0. Therefore, the blue curve cannot be the derivative of the red curve. And we conclude that the blue curve is the antiderivative and the red curve is the function. The following result is a consequence of the mean value theorem for differentiation. We have the following. If small case f is a function defined on an interval, and capital Case f and capital Case g are both antiderivatives of the function small case f, then capital Case f is g plus a constant capital Case c, for some constant c. To prove this, we have to show that capital Case f minus capital Case g is a constant. So since capital Case f prime is f and capital Case g prime is f as well, we conclude that the derivative of the function capital Case f minus capital Case g is f minus f, which is 0. By the mean value theorem, we conclude that the function capital Case f minus capital Case g is a constant. We denote that constant by c. And this means that capital Case f is g plus the constant c. Here it is important that the function small case f is defined on an interval. For example, the function 1 over x is defined for x positive and for x negative. And for that particular function, the same result does not hold. We will discuss that later more in detail. So if the function small case f is defined on a single interval, and capital case F and capital case G are both antiderivatives, then capital case F is capital case G plus some constant. From the table of derivatives, we get immediately our first table of antiderivatives. An antiderivative of x to the power p, when p is different from -1, is x to the power p plus 1 divided by p plus 1. If p equals -1, p plus 1 is 0, and therefore we cannot divide by that. Therefore this formula applies only when p is different from -1. But the function 1 over x corresponding the value p equals -1 has an antiderivative which is log of absolute value of x. This is defined for both x positive and x negative. We will discuss this just in a moment. Antiderivative of sine is negative cosine. Antiderivative of 1 divided by square root of 1 minus x squared is arcsine of x. Antiderivative of cosine is sine. The function a to the power x is defined only if a is positive. If a equals 1, a to the power x is always simply 1. That's a special case. If a is positive and different from 1, then an antiderivative of a to the power x is a to the power x divided by log of a. This comes out immediately from the differentiation formula for the function a to the power x. If a is e, the base of natural logarithm, then we have that an antiderivative of the function e to the power x is e to the power x itself, because then ln of a would be ln of e, which is 1. Antiderivative of 1 over cosine squared is tangent, and antiderivative of 1 divided by 1 plus x squared is arctangent of x. This table one has to remember by heart. More generally, if capital case f is an antiderivative of a function small case f, capital case G, that of small case g, and a and b are numbers, then the function a times capital case f plus b times capital case g is an antiderivative of the function a times f plus b times g. And this is immediate consequence of a formula for differentiation. So derivative of the function a times capital case f plus b times capital case g is first the derivative of a times f plus derivative of b times g. The constants a and b come out of differentiation, so this is a times derivative of capital case f plus b times derivative of capital case g, and that is simply a times f plus b times g. Using this last general property, it is easy to figure out that an antiderivative of the function 2 times sine of x plus pi divided by 1 plus x squared is minus 2 times cosine of x plus pi times arctangent of x. This is an antiderivative, and it follows, since negative cosine is an antiderivative of sine, and arctangent of x is an antiderivative of 1 divided by 1 plus x squared. Since the function 2 times sine of x plus pi divided by 1 plus x squared is defined for all values of x, it is defined on an interval. Therefore, all of its antiderivatives are of this form, this special antiderivative that we figured out plus a constant, that is minus 2 times cosine of x plus pi times arctangent of x plus capital case C, where capital case C is a constant. We have that derivative of log of x, natural logarithm of x, is 1 divided by x. But this is defined only if x is positive. For negative values of x, we may consider log of negative of x. Log of negative of x is a function whose derivative is 1 divided by minus x times derivative of minus x, which is minus 1. So we have that derivative of ln of minus x is 1 divided by minus x times minus 1. The minus signs cancel out. It is just 1 divided by x. We conclude that the function log of absolute value of x is an antiderivative of the function 1 divided by x, simply by verifying that the derivatives of natural logarithm of the absolute value of x for x positive and for x negative yield 1 over x. Now, the function log of x and 1 over x, they are defined only for x positive or x negative. They are undefined for x equals 0. From this it follows that all antiderivatives of the function 1 over x are of the form log of x plus some constant c1 when x is positive, and log of minus x plus some other constant c2 when x is negative. So c1 and c2 are constants. They may be the same, but they do not need to be the same. Any function capital F of this form is an antiderivative of the function 1 over x, and this family of functions contains all antiderivatives of the function 1 over x. We have established that an antiderivative of the function x to the power p, when p is different from negative 1, is x to the power p plus 1 divided by p plus 1, and if p is negative 1, then x to the power p is 1 over x, and its antiderivative is log of absolute value of x. Observe that for x to the power p to be defined for all values of p, we must assume that x is positive. Since, for example, if p is negative 1/2, then x to the power p is 1 divided by square root of x. And square root of x is defined only if x is non-negative, and 1 over square root of x is defined only if x is positive. So this function x to the power p is defined only for positive values of x in general. For particular values of p, of course, x to the power p is defined for all x. It may appear strange that the antiderivative of x to the power p is a monomial if p is different from negative 1, and it is the logarithm is p is negative 1. They appear to be of rather different kind of functions. This difference is superficial only, however. Namely, we observe that since x to the power p plus 1 divided by p plus 1 is an antiderivative of x to the power p, also any function which is obtained from this function by adding a constant is still an antiderivative. And now we add the constant minus 1 divided by p plus 1. So we observe that the function x to the power p plus 1 minus 1 divided by p plus 1 is also an antiderivative of the function x to the power p, assuming that p is different from negative 1. Now we assume that x is positive, and we consider the limit as p approaches negative 1 of the function x to the power p plus 1 minus 1 divided by p plus 1. Now p is our variable, and x is viewed to be a constant positive number. So when p approaches negative 1, x to the power p plus 1 approaches x to the power 0. Since x was assumed to be positive, x to the power 0 is just 1. So the numerator approaches 1 minus 1, which is 0. And the denominator p plus 1, of course, approaches also 0 as p approaches negative 1. We conclude that we may use L'Hopital's formula to compute this limit. And by L'Hopital, we observe that this limit is same as the limit as p approaches negative 1 of the derivative ddp of the quantity x to the power p plus 1 minus 1 divided by the derivative ddp of p plus 1. The derivative ddp of p plus 1 is just 1, and the derivative of x to the power p plus 1 minus 1 with respect to p is x to the power p plus 1 times log of x. So we conclude that the limit as p approaches negative 1 of x to the power p plus 1 minus 1, and that divided by p plus 1, is the same as the limit as p approaches negative 1 of x to the power p plus 1 times log of x. As p approaches negative 1, p plus 1 approaches 0, so x to the power p plus 1 approaches x to the power 0, which is just 1 because we assume that x is positive. Therefore, this limit is log of x. And we were able to find a family of antiderivatives to functions x to the power p when p is different from negative 1, which family has the limit log of x as p approaches negative 1. So these two antiderivatives, after all, are not so different. In view of the remarks just made, the table of antiderivatives obtained from the table of derivatives should be written in the following way. For the function x to the power p when p is different from negative 1, an antiderivative is x to the power p plus 1 divided by p plus 1 minus 1 divided by p plus 1. Of course, this term minus 1 divided by p plus 1 can be also left out because it is just an additional constant. But if we do this change and consider these special antiderivatives, then as we just obtained, the limit of these functions as p approaches negative 1 is log of x, which is an antiderivative of 1 over x. An antiderivative of sine is negative cosine. An antiderivative of 1 divided by square root of 1 minus x squared is arcsine of x. Antiderivative of cosine is sine. Antiderivative of a to the power x when a is positive and different from 1 is a to the power x divided by log of a. Antiderivative of 1 divided by cos squared of x is tangent of x, and an antiderivative of 1 divided by 1 plus x squared is arctangent of x. One needs to remember this table by heart, and observe also that the formula for the antiderivative of the function a to the power x contains as a special case the antiderivative for the exponential function e to the power x. Its antiderivative is e to the power x divided by log of e, but log of e is 1, so antiderivative of the exponential function e to the power x is that function itself.